Alright, so let's continue to look at a couple of the series. So for this one, 2n over 5n plus 6 to the power of n. And this format actually is perfect for root test. Okay. So if we apply the nth root of absolute weight of an, that is nth root of 2 and 5n plus 6 to the power n. Turns out this is 2n over 5n plus 6. As you take a limit n goes to infinity, this can give you 2 over 5. And based on the root test, 2 over 5 actually less than 1. So we can get that this series, it converges, okay? Not only converges, but also it converges absolutely, okay? So let's use the root test. Now look at the other one. So it's negative 1 to the power n plus 2, n squared, e to the power of negative 11n, okay? So this is too small. Okay, so that's a problem. Now we can try a couple of them. We can do ratio. We can also do a root test. So why don't we do ratio this time? Because the above one we just did with the root test. So ratio test is absolute value of plus 1 over an, right? So that is negative 1 to the power n plus 3, n plus 1 squared, e to the power negative 11, n plus 1, over negative 1 to the power n plus 2, n squared, e to the power negative 11n, okay? Of course, we need to put an absolute value here. So it turns out that we can drop this alternating term because we have the absolute value. And also, we have it n plus 1 squared over n squared, and then time e to the power of negative 11, okay? Because e to the power of negative 11 is all cancelled out. Now, if you take the limit as n goes to infinity, turns out this part going to be 1. So we have e to the power of negative 11. And it's very easy to show that, or to observe that, e to the power negative 11 is less than 1. Hence, based on the ratio test, we can also get a conclusion that this series converges, okay? So as one use the root, the other use the ratio, okay? So now let's look at another couple of extra examples here. Now look at this. This is n factorial times negative e to the power of negative 24n. Okay. So for this one, the best approach is going to be ratio test. Why? Because you have this factorial. Okay, you have this factorial. So the ratio give us is n plus 1 factorial, negative e, negative 24, n plus 1, okay, over n factorial, negative e, negative 24n, okay. So it turns out, so n plus 1 factorial equals n factorial times n plus 1. Okay. So after a simplification, I have n plus 1 times, actually it's negative e to the power of negative 24. Okay. So this is what we got. Okay. Now, do you agree? Oh, maybe put a parenthesis here. So do you see that actually this is a constant, okay? And this one is going to n plus 1. As you can see, as n goes to infinity, this limit, it also goes to infinity, okay? That means what? That means, well, based on the ratio test, my series actually diverges. Okay, diverges. Okay. So this is the this problem. Now let's look at the other one. So this problem, it's let me write it larger. So it's 3 to the power of n and factorial n square. Okay, n square. So you know if we reorganize this, it's gonna be 3n factorial, right? N over n square n, right? Even more, right? We can write into this way. So it will be good to use root test because we can cancel this to the power of n. Okay. So root test is nth root of this, right? 3n factorial n squared to the power n. It turns out this is going to be 3n factorial over n squared. Okay. So for this, as you can see that as n goes to infinity, this limit also going to goes to infinity. Okay. Why? Because you can think of this 3n factorial is 3 times n minus 2 factorial times n minus 1 and times n, okay? And then over n squared. So as n goes to infinity, actually this part going to becomes into 1, but this part going to become larger and larger. So that's why, you know, you get that this limit, as n goes to infinity, it goes to infinity, okay? So that explain this goes to infinity. Okay, so that's a short explanation. So that shows that the series actually diverges also. Okay. Now, next. This one should be pretty straightforward, right? So it's negative 1 to the power of n squared, 7 over 2 to the power of n here. We can still do ratio, but I think root also will work. And also the ratio, root, and the alternating series test also work, I believe. You know, but I'm lazy, so maybe let's do root test. So the nth root, absolute value of this, it will give me the nth root of n squared times 7 over 2. Okay. So it turns out that as n goes to infinity, the nth root of n actually is 1, and you square that, still 1. So this gives us 7 over 2. This is less than 1. So based on the root test, this series converges. Okay, converges. So now let's look at you know, the other problem here. We have series here, and then I'm asking to figure out the series radius and the interval of convergence. So we can use ratio or root. Doesn't matter. So we can use the maybe ratio again. So negative 1 to the power n plus 1, 3x minus 7 n plus 1, negative 1n, 3x minus 7 n, right? Turns out we're going to have its absolute value of 3x minus 7. Okay. So based on a ratio test, if this is less than 1, so we can get that actually this is going to be the 3x minus 7 less than 1 greater than negative 1, so 3x is less than 8, greater than 6, so x is less than 8 over 3, greater than 6 over 3. Okay, so that's the interval of convergence. And of course, the 6 over 3. So the radius of convergence actually going to be 8 over 3 minus 6 over 3 and then half it, right? So it turns out it's going to be 1 over 3, okay? 1 over 3. So that is the radius of convergence. Then for what value of x it converges absolutely? For sure, we know that based on the ratio test. So when x is greater than this, less than this, it converges absolutely. So the last part, there's a typo here. The prob asks, so for what value of x does the series converges conditionally? Okay. So for this part, we need to verify at the two endpoints what happened. The reason is to use either as ratio or root test when we denote, we denote capital L as, the ratio here. When capital L is less than 1, is absolute convergent. But when capital L equals 1, there is no conclusion. So that means that we really need to verify at two endpoints whether they are converge or diverge. Okay? So when x equals 6 over 3, which is true here, so if you plug in that, the series becomes negative 1 to the power of n. So 2 times 3 is 6 minus 7 is negative 1, so it's negative 1 to the power n. Turns out this is series 1. Okay. Now this series, it diverges. Okay, it diverges. When x equals 8 over 3, that series becomes into negative 1 to the power n times, if you plug in 8 over 3 in, it's going to give you 8 minus 7, so that's 1. So this series also diverges, okay, diverges. That means what? That means actually there is no value that are gonna converges conditionally, okay? So all the value lies on this interval, it converges, and it converges absolutely, okay? So that will solve this problem here. So it's a pretty long video, and I hope you enjoy this couple of series examples, okay? So thank you for the watching.